Hello and welcome to my presentation about the influence of materials on the behavior of joints with multiple bar connections. My name is Patrick Heinemann and I'm a PhD student of the George Azaki University of Iași. Tubular steel joints are mainly used in industrial or extravagant structures because of the high stability resistance and at the same time of the low weight. There are several hollow section profiles which can be used, like squared hollow section profiles, rectangular hollow sections, or circular hollow sections. The joints of these hollow section profiles are the weakest area because of the heterogeneity of the geometry and the material. You have, for example, the welding line in this area. On the right hand side you have a table or a figure of different joint types. It's an extraction of the standard Eurocode. In this area of the welding, you have got mainly three types of stresses. The first is nominal stress. It's because of the force which is induced. Secondly, there's a geometrical stress due to the heterogeneity of the structure. And the third part is the local stress, which is induced due to the quality of the welding, for example, if there are some imperfections and so on. To increase the resistance of these joints, it's one possibility to change the overall material or only to change partly the material. In the following, I want to show you some different materials. The first material I want to present is the stainless steel. Times now it's an underpart for industrial purpose, but there are some advantages like high resistance to corrosion, ductility, stiffness, strength, recyclability, and aesthetics. The most common type is the austenitic duplex ferritic. Mainly circular hollow section profiles are used. The current design code, which is the Eurocode, is a little bit conservative regarding stainless steel. Feng, for example, also said that a joint which is done out of circular to squared hollow section profiles are in the Eurocode not appropriate for the T, Y, and X joints. The second material is the high or the low strength steel. It's the easiest method to change the material or to raise or to increase the stiffness is to variate the hardness of the steel. It is less expensive than stainless steel or aluminum, and the current design code includes a steel up to 700 megapascal. Truss girnders of long spans are, for example, or can be found in sport arenas or bridges, something like that. Especially for high-strength steel, the secondary bending moment is relevant. Or with other words, in systems with a large beta value, the beta value is defined as brace to chord diameter ratio. Large secondary bending stresses can arise. Xing found out that the ultimate load resistance can be increased by 20 to 142% depending on the steel grade for or in case of high strength steel. The third material is timber. Timber is a quite special material. It is lightweight and ecological material. It can be integrated quite easily in nature settings. but it's an hybrid material. So the joints cannot be made directly out of wood. There must be some other structures. On the bottom of the page you can see two figures as an example. In this case there are some steel constructions for the joints. So you have to make sure that wood members are only in axial tension or compression. Lokai did a study about the influence of the inclination angle of these wood structures. In this case about 0, 60 and 90 degrees inclination angle. The inclination angle is defined by the angle between the brace and the cord. On the right hand side you can see on the top the results for a round timber shape, and yeah, it can be seen that for the 60 and 90 degrees the results are quite similar, and the 0 degrees are a little bit more different. Down you can see the squared, or the results for the squared timber shapes, and there the results are not really comparable. The next material is a carbon fiber reinforced polymer, or easy carbon. It is a composite material made out of a matrix and a reinforcement. So it's made out of many very small carbon fibers. For industrial purpose it's too expensive, but the advantage are the low weight and the high strength. It has got a high resistance to corrosion, and Jiao and Zhao even told us that there are an increasement of 25 to 76% in the tensile strength. Dong even concluded with better results for circular hollow section to squared hollow sections, and carbon has got a significant effect on lateral deformation and local buckling. A very special opportunity is to use concrete filled steel tubular elements. And you can imagine it's a tubular steel hollow section, for example circular hollow profile, and it's filled up with concrete. You can automatically get a higher stability, and it's used for large diameter hollow section geometries like in the offshore field. It has got high resistance to corrosion and to fire. And Sale occurs different failure modes for the circular hollow section K-joint, and for example punching into the cord or local buckling. He concluded that the corrosion has only a moderate effect on the behavior of the joint. In the past I did some studies about the influence of the materials on the behavior of the joint. Mainly I did two numerical studies about the Van Mises stress, strain and deformation. The models were about 6 materials. I tested aluminum, stainless steel, steel with high and low ratio of carbon, carbon itself, and the steel grade S235, which is one of the most common steel types in Europe. On the right hand side you can see a table with the material properties I used. Timber was excluded in these studies because of the heterogeneity of the material. I used Y and a K joint, which were made out of the 60 degrees circular hollow section profile. The cord was set as pinned, and has got a larger diameter of a DN50, and the brace is one step smaller with a DN40. The length is set to 350 millimeters. I used quadratic tetrahedral solid elements, so a 3D or a three-dimensional system. On the right hand side you can see the mesh. So there was a 10 millimeter coarser mesh, and in the area of the welding I set 1.3 millimeter refined mesh. Generally I used 3 millimeter fillet weld. The braces were affected by a 20 kilonewton axial tension force for each brace. The results between the stress, deformation and strain were quite or are comparable. So for each steel they are quite the same. There is a gap between the K and the Y joint, and in case of aluminum there's a little peak, so if you want it's a little bit weaker, and there's a higher peak for the carbon. So yeah, the carbon is a very special case because it's more a theoretical study. So it's yeah, because of the composite material, it's not quite comparable because of the welding. In a normal case, you don't weld a carbon structure in this with a fillet weld, for example. To come to the conclusion, I showed you the advantage and disadvantages of different materials. I set it 6 different materials, and the general aim was to increase the resistance and stability of normal used industrial steel. Carbon especially is too expensive for industrial purpose. I did numerical studies about Y and K joints. In case of the stresses, the different steel grades are nearly superimposable. The aluminum has got a lower resistance, and the carbon is only a theoretical model because the concept of the fillet weld is not applicable for composite materials. Yeah, I want to thank you for listening, and see you.